Welcome back. This is the fourth of 5 tutorials that will help us get started in R. Last week we used bracket subsetting to select pieces of the data that we wanted to work with. While this is great, it can start to become difficult once we get into more complicated operations. This week we'll be using packages called dplyr and tidyr that make it a lot easier to select specific parts of our data and to do some of the most common things with our data frame. The first thing I want to do is get my R sessions set up. Instead of creating a new project, I want to keep working in last week's project. I called this starting with data. So I'm going to navigate to the project folder and open up the project. This .rproj. Do you want to open the project? Yes. And I will create a new R script, and I'm going to Control S to save it as working with data. And there I see the new R script and the R script from last week. So the first thing that you will want to do is install the packages. The tidyverse package contains a few other packages, and instead of installing them one by one, we can install the tidyverse package. So go ahead and run this. And once you've installed, remember you only have to install packages once, and then in future sessions you can load the package using the library function. So library tidyverse. And we are going to import data. I'm going to import the data into an object called surveys. And instead of the read.csv function that we used last week, this is a built-in function, we're going to use the read_csv. This is from the tidyverse package. What this does is it recognizes columns that are characters, like species ID, as characters instead of converting them into factors. So read_my data is in this folder, data raw, so data_raw, and I'm going to look at the file name. It's portal data_join.csv. And I'm going to run using the keyboard shortcut. And I can see that just an information message that the columns were parsed. That means the comma was recognized and the following columns were identified. One of the first things we do when we import new data is we look at the data using those built-in functions like str. So let's look at the structure of surveys. I'm going to scroll up. So this is a tibble, which is a different kind of data frame. Is similar, and we use it in similar ways. And we can see that columns, number vectors, we have a character vector, and then this tells us about the parsing. Let's go ahead and view surveys. Remember, we could use the view function, or we could click the object name in our environment. And notice how the class of surveys contains this tibble data frame, these different kinds of notations. So tibbles modify some of the behaviors of data frame that we worked with last week. The data structure itself is very similar, and the only differences are that in addition to displaying the data type of each column under its name, it only prints the first few rows of data and only as many columns as fits on one screen. And these character columns are never converted into factors. So in this week, we'll learn some of the most common dplyr functions, which is a package inside of the tidyverse package, like select to subset columns instead of using the brackets, or group by and summarize to create summaries of our data. So let's start by selecting columns and filtering rows. To select columns of a data frame, we'll use the select function. The select, so the first argument to this function is the data frame. You see that in the yellow box, data, so surveys. And the subsequent arguments are the columns that you want to keep. So let's keep plot ID, species ID, and weight. Remember, this is the portal small mammal data, so they have information on the weights of individuals that have been trapped, as well as the species ID and which plot it comes from. Let's go ahead and run this command. And remember, if we had done this using the built-in functions, if we had ran output and not stored it in an object using built-in functions, it would have printed out the entire object. But instead, what we get is the first few rows. So when you're working with your neon data, if there's only specific columns that you want to work with, then you can use the select function. Last week, we saw how to subset using the bracket notation. So we saw how to call specific columns using their index or number position. And we also saw how to exclude certain columns. So let's see how we would do that using the tidyverse functions. So the first argument is the data you want to work with. So we want to work surveys, all columns except, look, we're using that minus sign notation again to indicate the columns that we don't want. So we're basically telling R, give me the columns from surveys, and the following columns that I want is not record ID and not species ID. In this above line where we were selecting columns, we were telling R, from surveys, give me the following columns: plot ID, species ID, and weight. And then here, from surveys, give me the following columns: not record ID, not species ID. So R understands that as give me all columns except these two. And you could continue if you wanted to exclude other columns like month or minus year. Let's go ahead and run that. Oh, and I have a typo. I get an error. Can't subset columns that don't exist. Column species ID F doesn't exist. That's because I accidentally hit the F key and and that column doesn't exist. So when I run this, now we can see we have all columns except, as well as weight, genus, species, taxa, plot type, and we don't see these columns. What about rows? We saw how to select columns and rows last week inside of those brackets. Remember the RC cola, the row, comma, column inside the brackets. This week we can use a filter function that makes it really easy. So from our surveys, I want to select all rows where year is 1995. This is helpful to choose rows based on a specific criteria. Notice how I had to use this double equal sign because the single equal sign means something else. It can mean the same as this assignment operator, and a single equal sign is confusing to R, and this is why the notation is to use the double equal sign. So give me all rows where year, that's the column name, is equal to 1995. So let's look at our data frame and see what we're asking R to do. So it's saying give me all the rows where year is 1995. So let's run this line, and now we see the rows, the observations that were collected in 1995. So what if we wanted to take this output and use it to do something else in the next step? To do that, we'll use this concept called pipes. Pipes allow us to use intermediate steps. And with intermediate steps, you create a temporary data frame and use that as input for the next function or the next line. So for example, let's see an example without pipes. So let's create surveys 2 where we can store or we can select rows based on some criteria from surveys. So from surveys, let's select all the rows where weight is less than 5. I'm going to run this. So now it's in our environment. I'll expand this. And then let's say we want to create another object that selects certain columns from surveys 2. So from surveys 2, select column species ID, sex, and weight. So I'm using the output of this line as the input of the subsequent line. This is perfectly fine. It's readable, it works. Remember, there's multiple ways of doing the same thing, getting the same output in R. However, when working with R code, you want to be as efficient as possible. You want to do the operation in as few lines as possible because this helps with overall readability of your code. It makes it easier for other people to understand, makes it easier for your future self to understand. This clutters up the workspace with lots of objects that you have to name individually, and you probably won't use the intermediate objects. And so you end up with lots of objects in your environment. With multiple steps, it can be hard to keep track of what object is what. Instead, let's nest our functions inside of each other like this. So let's surveys small SML underscore SML select. Let's select. Okay, I'm going to leave the data blank. Let's come back to that. But let's select species ID, sex, and weight columns, right? We want to select these columns. And in our data, let's use the filter surveys weight. This can be a little confusing and disorienting at first because there's so many different things going on. So let's look at this again. This code, right, the data that we want to select from is the equivalent of this new object we created. Right, we created this new object, said filter from surveys all the rows that are less than 5 for weight, that have a weight of less than 5. Right, that's the data that we created. Let's look at surveys too. Maybe that'll help make this more tangible. So let's look at the weight column. These are all the rows where weight was less than 5. So we're asking in this nested approach, we're creating this data without assigning it to an object. And then we're telling R, okay, from this data, pull out the following 3 columns. And this will be called our survey small. So in the above example, we did this in 2 steps. So it takes up 3 lines of code and this intermediate object. And in this line where we're nesting the functions inside of each other is a single, it's a single command. Another option is to use the pipes. Pipes are a pretty recent addition to R, and it allows us to take the output of one function and send it directly to the next. What I don't like about this is that there's so many things going on that it can be difficult to keep track of, and pipes make your code easier to understand. If you use RStudio, you can type the pipe with the keyboard shortcuts Control-Shift-M if you have a PC, or it's Command-Shift-M if you have a Mac. So Control-Shift-M is the keyboard shortcut, or Command-Shift-M for a Mac. So let's use pipes instead. Let's say, okay, from our surveys object, I'm going to use the keyboard shortcut to get that pipe notation. And I'm going to select enter, and it will automatically indent the next line of code because, and the red X icon will appear, and that's a sign that our command isn't complete because R expects additional code after the pipe. So we would have to provide it with an additional line. So let's use our filter, this line here, but because pipes understand that the data comes from the previous line, we don't have to provide the data like we did in this line. We don't have to tell R that we're working with the surveys object. It understands, and all we need to provide is the the selection that we're interested in. So from surveys, filter rows where weight is less than 5, and I'm going to use the pipe again. It'll automatically indent, and then select the following columns: species, underscore ID, sex, and weight. And I should be using spaces after my columns because it helps with readability. So let me extend this a little bit so we can compare the 3 different methods. In this, we use the built-in abilities of R to first filter and then select. So we have this intermediate object. In this example, we nested our functions inside of each other. And in the third example, we used pipes. So I don't know about you, but for me, this is a lot easier to read. It's consecutive, and it just looks nicer. It's easier to understand too. So we're telling R from our surveys, use our surveys objects to filter rows where weight is less than 5, then use that to select, then use this filtered data to select these 3 columns from this filtered data that was created. So we send the surveys data set first through filter to keep rows where weight is less than 5, then through select to keep only these 3 columns. Since the pipes takes the object on its left and passes it as the first argument to the function on the right, we don't have to include the data frame as an argument to the filter and select functions. I find it helpful to read the pipe like the word then. So take surveys, then filter, then select. So we actually haven't run this command. Let's go ahead and do that. I'll expand this. We can see, scroll up a little bit. And so our output is printed in the console because we didn't save this as an object. So if we wanted to save this as just an object, we would assign it an object name, just like we're getting used to doing. So I'm going to run this again. And now our survey small is there. And if I wanted to view that object in the console, I could print it in the console. So there's 17 rows and 3 columns. In this week's assignment, you are being asked to subset the surveys data to include mammals that were collected before 1995 and to retain only the columns year, sex, and weight. So instead of weight less than 5, you will write year is less than 1995, right? Because those are rows where year is before 1995, and then you'll modify these to the columns that you're being asked to retain. All right, let's look at another useful function called mutate. A lot of the times you'll want to create new columns based on the values of existing columns. If you know how to do this in Excel, you can you do this by using formulas. But we'll take a look at how to do this in R. So let's say we wanted to create a new column of weight in kilograms. Our current column weight is in grams. So to create a new column, I'm going to take our surveys use our pipe. So take our surveys object, then mutate this data. And because I'm using pipes, I don't have to designate the first argument as the object. And instead, I can create a new variable called weight kilograms, which is equal to weight divided by 1,000. So this is the name of an existing column in surveys, and this is the name of the new column. So let's go ahead and run that, and I'll scroll up, and we actually can't see it, so I'm going to let's store this as a new object. That way we can see the entire data frame. So here is our weight, and there's no value here, so there's no value in our new column. But if I scroll down a little bit, now we see our grams in kilograms. Let's say we aren't used to thinking about weight in kilograms, so we also want to create a new column, another column called weight pounds. We can do that by adding on to our mutate function. So weight pounds would be weight kilograms times 2.2. So notice how, you could keep this code all in the same line, but it makes it easier to read if you indent after the commas. And R will automatically indent the code to make it nice and readable. Because our data frame is getting a little big, let's pipe this into the head function. And because we're using pipes, it understands the head function as referring to the data that came before, the lines that came before. So we don't have to tell R what goes inside this head function, what data to view the first few rows, the first 6 rows, because it understands that this pipe refers to everything on the left. And because I'm storing this, it won't print. So I want to just print it. I want to print it in the console. And we see the additional columns below. And let's see. Let's go ahead and look at our surveys 2. It was our weight. Well, we started as weight kg, and where we saw that there's rows where there is no value for weight. So let's say we wanted to filter out those NA rows. So we would add the filter function, exclamation point for is not. Remember last week we used the exclamation point and the equal sign. Here, I'll write it here. Remember we used is not equal to. In this case, we can use it to indicate is not NA for the following columns, and we would have to use that pipe again. So we're telling R, take our surveys data, then filter all rows that are not NA in the weight column, then mutate this filtered data by adding two new columns called weight underscore kg and weight underscore pound. And their values are the weight column divided by 1,000 for each row. And then take this column and display the first 6 rows. So I'm going to go ahead and run this. And now there will be no NA values in our weight column. So it's filtered out all the rows where weight was equal to NA. In the assignment, you are being asked to create a new data frame from the survey's data that contains only species ID column and a new column called hindfoot centimeters, where the hindfoot length values have been converted to centimeters. And you don't want this new column to have any NAs, and you want only values that are less than 3. So I'll set you up and then you'll fill in the rest. So let's create this new object, and inside that object we'll store the results of our selecting and filtering rows. So from our surveys pipe, Control-Shift-M, you want to filter on the hindfoot length. So you want all the rows that are not NA in the hindfoot length column. Then you want to mutate, you want to create a new column called hindfoot centimeters, similar to what we created here. So you'll convert hindfoot length to centimeters. And you should know that hindfoot length, I'll give the units of hindfoot length. Then on this new data, this new column, you want to filter all the rows where hindfoot in centimeters is less than 3. So it'll look similar to this, where we selected weight was less than 5. Then you want to select only the 2 columns, species ID and your new column that you created, hindfoot in centimeters. So you might want to pause the video and continue working on this, and then come back when you're ready. There's one more function that I'd like to demonstrate because I use it very often. This is the summarize function in combination with the group by function. They're used together to collapse each group into a single row where you summarize by that group. That may not mean anything to you, so let's see an example of this, and maybe it'll become more tangible. Let's select our surveys object. So we want to work with our surveys object. Control-Shift-M for our pipes. Then we want to group our surveys object by sex. Then we want to summarize mean weight. This is a new variable, which is equal to mean of weight, the weight column. And remember how if we were to write, let me see if I can do this. So mean surveys, $ to indicate the column weight, if we were to run this mean function on this weight column, we receive an NA because there are rows in our weight column that are NA, and R does not know how to calculate the mean for when there's NA values, right? Like 3 plus 4 plus 5 plus NA divided by however number of entries there are produces an NA value. So we have to remove those NAs using the argument na.rm equals true. Let's go ahead and run this line, and we'll see now the group summary. So we've grouped by sex, so we have 3 groups: F for female, M for male, and NA for where sex wasn't recorded. These are the rows where sex wasn't recorded. And then we've created this new variable called mean weight and calculated the mean weight for each of these groups. I think this is pretty useful. You can definitely imagine using this in the NEON data if you're interested in, some variable by a group, by site, maybe by date. You could group by date. You could group by species. So you can imagine how you would use this with the NEON data. Maybe you wanted to group by multiple columns. You can do that by indicating the columns you want to group by inside this group by function. So now we have our mean weight is summarized by sex and species ID. So let me expand this so we can see the entire output. So we have female for species BA, female for species DM, and if we saw the entire output, we would also see male for species BA, male for species DM, and their different weights. So maybe you're interested in using the small mammal trap, and you can do a similar analysis. So this prints out the first few entries, but what if we wanted to see the last few entries? We would add the tail function to the end of this series of pipes. And now we can see, I was hoping we would see the M's, but the N alphabetically, N is after M, and so our last entries are for groups where no sex was entered for the different species. And of course, in these, there was also it looks like there was no weight recorded for this group. You can imagine this could be maybe the specimen escaped before their sex and body weights could be determined. And that's why the resulting mean weight column does not contain NA, but this NaN, which refers to not a number, because the mean function was called on a vector of NA values, while at the same time setting NA.remove to true. So to avoid this, let's add another selection. Let's add at the very beginning, filter all these columns that are not NA in our weight column. And I need to add a pipe there, group by, summarize. So now we filtered out all of those values first for weight that were NA. Then we grouped by these two columns. You could add more columns if you wanted to. Then we summarized by mean weight. Let's say we want to see more columns than what's printed. We can use the print function and tell it how many rows that we want R to print. So here R is printing 30 rows. If we scroll up, now we can see the sex female for species BA. And if we scroll down, hopefully we see the male sex for species BA. And they have different mean weights, so 7.36 and 9.16. It's fairly common in the natural world that female and male organisms have different body size. And that's because of different reproductive requirements. For females, reproduction is more energetically expensive, takes more energy, and so females tend to be smaller because they're putting more energy into reproduction. At least in mammals. It's a little bit different in other organisms. Okay, sorry about that quick tangent. Let's continue on by working with our series of pipes. Let's say we wanted to summarize multiple variables at the same time. I'm going to expand this so it all fits on the same line. For instance, let's add a column indicating the minimum weight for each species for each sex. So we would add this to our summarize function and create a new variable called min weight, a new column, and that would be min. We use the min function, and it's saying that there's an error expected, that it expects a comma after the expression. Right. And I'm checking my parentheses. I'm doing some accounting. Comma, new column, close parentheses. This closes the summarize function. Sometimes it's useful to rearrange the result of a query to inspect the values. For instance, we could add another line here called using the arrange function on the new column that was created. Let's go ahead and run this, and I'll scroll up, and now we can see, in addition to the mean weight column we created, now there's the min weight, and we can see the minimum weight for each of these groups that we were interested in. And it's arranged by minimum weight. So this goes in order from smallest to largest. To sort in descending order, maybe we're more interested in the larger values. We can use a nested function called descending. So notice how I use this function inside of the arrange. So I'm telling R, take all of these filtered, grouped, and summarized data and arrange it in descending order for min weight. And let's go ahead and run this. And I'll scroll up. So now we have the min weight column arranged in descending order. So largest values first. Many times when working with data, we want to know the number of observations found for each factor or group. And for this task, we can use the a count function. Let's take our surveys data, then count the number of entries by sex. And now this automatically counts the number of entries for each of these factors. So female, male, and NAs. So it's pretty evenly split between male and female. The count function is shorthand for something we've already seen, this grouping by a variable and then summarizing it by counting the number of observations in that group. In other words, surveys pipe count sex is equivalent to surveys pipe group by sex, then summarize it, making a new column called count, which is equal to n. So n, if we question mark n, we can see gives the current group size. So the count function is pretty convenient because in 2 lines of code, you can do what 3 lines of code would do. Let's say you want to count by multiple groups, like sex and species, like we were doing above. Let's go ahead and run this. Now we see the sex by species, and actually this should be species ID to match what we were doing above. Oops, and now we see that same grouping, sex, species, count. Now we have this n column, and if we wanted to arrange our groups by the number, we could, let's say, okay, take this count by these 2 groups and arrange the output by species and by descending value of n. So now we're arranging by 2 columns. I'm going to run that. Oh, and that's because I get an error message that there is something wrong, and that's a cue for me to look at my code, and that's because I use species instead of species ID. So there's actually there's no column called species after I change the species ID. So I'll rerun this, and now I can see we've produced this group by sex and species ID, as well as the numbers in each of these groups, and we've arranged by species and count in descending order. In the exercise, you are being asked to count the number of animals caught in each plot type. So instead of sex, you want to enter the column name for plot type. You are also then asked to use group by and summarize to find mean, min, and max hindfoot length for each species and add the number of observations. So let me set that up and then you can fill in the rest. So let's take our surveys object. Then we want to filter, because we want to calculate mean, min, and max. Remember, those functions don't work with NAs, so we want to filter is not NA for hindfoot length. So go ahead and fill that in. Then we want to group by species ID. And then we want to use the summarize function to calculate four new variables: mean hindfoot length equals, and I'll let you fill that in. Then we want, because I didn't enter something here, okay, you'll have to fill in what goes inside the mean function. We want min. We want a new variable called min hindfoot length using the min function. And I'm missing my commas here. We want a new variable or column called max hindfoot length using the max function, and we want the count using the count function. And that's the closed parentheses for my summarize. So I want to summarize on this. All right, so if you want to pause the video and fill these in, go ahead and do that, and then come back when you're ready. The last exercise, you're being asked to figure out the heaviest animal measured in each year. And you want to return specific columns. So I'll get you set up and then you can fill in the rest. So we want to take our surveys data, and remember we want to filter all the NAs and weight. So this line will be the same as what you put in here. Then we want to group by a variable. Go back to the question, right? What's the heaviest animal measured in each year? So you probably want to put year in here. Then we want to filter on column weight for the maximum weight. Then we want to select the columns, so the column names will go in here. And maybe you don't have to do this last step, but maybe you want to arrange those by year. The last concept I want to demonstrate is how to export data from R into a new CSV file. Let's start by creating a new object called surveys underscore complete, and inside that we're going to assign the values from this series of pipes. So take our surveys data, then let's filter out all of the rows where there's NAs for weight, hindfoot length, and sex. And this will be like the complete data set where these three columns or variables have complete information, so there are no NAs. So let's say is.NA weight, filter out all values where weight is NA. So I don't want NA values for weight, hindfoot length, comma, exclamation, is.NA, sex. So I'm saying, okay, R, take my surveys data frame, then filter for rows that are not NA for weight, hindfoot length, and sex. And store this in surveys complete. Now I want to look at surveys complete. So this is observations that have the complete data for these three variables. So there's no NAs in these three columns. And if we want to export this, then we can use the tidyverse function write underscore CSV, surveys complete, and I'll go back to my files. I'll go back to my project folder, and we don't want to save our modified data in the same folder as our raw data. So I'm going to create a new folder called data. And if you want to add modified data to help you remember, that's great too. And then we can give it the path, which is data folder / and it's called, we want to call it maybe the same name, surveys complete, and we need to provide the extension, so .csv. This argument is called path, but R expects the path name to be the second argument. So in those cases, we don't have to designate the path. We don't have to write out path equals because R expects the path here. If you want to include it to help you remember, that is good too. So let's go ahead and run this. And now inside of our data folder, we have this exported data. So that is it for this week. It's a whopper of a week. This is the hardest week, and then things get a little bit easier, and we'll start working with our neon data to do these kinds of analyses. So hang in there. You're doing amazing. Slow it down if you need to go back to the exercises, and if you have questions, post them on our discussion board. So nice work.